Welcome back, children. In this video, we are going to see what happens when you keep a magnet. It could be a bar magnet or a current carrying solenoid or any other magnet in an external magnetic field. Let me first draw the picture and then we will continue our discussion. This is a magnetic field. This is the external magnetic field. Let's say I have a field like this. And now I am going to keep a magnet like this. This is my bar magnet, let's say. So this is going to align with this field. Okay. So this is my north and this is going to be my south. So this is how it is aligned. So this is my B. This external magnet, this is not the magnetic field of this bar magnet. Notice that this is the external magnetic field. There is a magnetic field. I am going to keep the bar magnet in that field. Okay. And now if I push it this way straight, then it will keep going that way. But that is not what I am going to do now. I am going to hold it, in the sense like I am going to suspend it maybe in this field. So I will not allow it to move in this direction. I am going to hold it like that, suspend it. And then I move it, I push it in this direction, I disturb it so that it goes like that. What I mean by that is, this magnet now goes like this. Okay, so there is this angle theta. Okay, so what will happen? The magnet is like this. The magnet is something like this, Now I push it like that. I just slightly disturb it and leave it. Then what will happen? This magnet will be pulled back by this magnetic field, then it will start coming back to this position. But then will it stop here? No. As it comes back, it would have gained some speed, which is not zero at this point, so it will overshoot this position. As it overshoots, it will come here. As it comes here, then it keeps pulling back in this direction, in the opposite direction, pulls back. This field pulls back the magnet in the opposite direction, so the speed becomes zero, and then it will go back again. Again, it will gain some velocity as it comes here. Would it stop? No, it wouldn't. It will overshoot again. So this will keep oscillating. This oscillation will go on forever if there is no damping force, if there is no friction or any other force that damps this oscillation. It will keep oscillating forever. Previously it was in equilibrium, now we have slightly disturbed it and it will keep oscillating from that position. So this is what will happen. I can demonstrate that to you with a simple bar arrangement. So I have a bar magnet here. So this is north pole. So let me hang it. Okay. So the north pole is here. So it's aligned to the north pole of the Earth. The Earth itself is a giant magnet. Now this is kept in the external field of the Earth magnet. So Earth magnet produces a field, and I have kept this magnet in the external field of the Earth magnet. So all of us are immersed, right, in the Earth's magnetic field. So anyway, this bar magnet is now in the Earth magnetic field. Okay. Now it stops. Now if I slightly disturb it and if I leave it, I notice that it keeps oscillating. So what I disturb it now, I leave it, then it keeps oscillating. You can see that. So that is what I was telling you when I explained this. Okay, so why does it oscillate? It oscillates because there is a restoring torque. I moved it. Okay, here it is like this. I moved it to this position and I left it. So there is a restoring torque given by the external magnetic field. So that brings it back. Then what would be the value of the torque acting on this bar magnet? And that would be, so tau, okay, I put the vector sign now, to the torque is equal to, as we already know, m cross b. This m is the magnetic dipole moment of the bar magnet, and this b is the field strength of the external magnetic field. Okay, so if I move it to an angle theta, then the magnitude is given by m b sine theta. But notice that there is a restoring torque. So the greater the angle, see the change in angle is in this direction. Notice? So I kept it here, then I move it this way. The change in angle is in this direction. Okay. But what about the torque? M would be in this direction, right? It's north pole, so M would be in this direction. This would be the direction of M. And this is the direction of B is in this direction. So M cross B will go into the pole. So your d theta, the change in angle, the theta would be in this direction, but then your the torque, the restoring torque due to this field would be in this direction, in the opposite direction. So if you have a positive value for theta, then torque would be, will have a negative value. It's a restoring torque. So now I will say that tau is equal to minus ma theta. It is negative. Okay. I want you to understand this. This is a restoring torque. So this has a negative sign here. Torque is equal to minus ma theta. This is the magnitude of the torque, but then it's a restoring torque, so it has a negative sign. So there is this oscillation that is taking place. Okay. Let's put it this way. Let's take this sine theta for example. For very small angles from 0 to say 15 to 20 degrees, then for very small angles, we have already come across what is called as a small angle approximation, which is sine theta is equal to theta, and which is also equal to tan theta. So for very small angles, we know that sine for very small angles, sine theta is approximately equal to theta, and that is also approximately equal to tan theta. But we are not bothered about tan theta here, but we have sine theta. So sine theta can be treated to be approximately equal to theta if the angle is small. That is very important. So tau is equal to minus m b sine theta. I'm going to write theta. In this case, theta must be in radians. Don't take the theta value to be in degrees. It's in radians now. So tau is equal to minus mb theta. So there is a torque which is acting on this body. Then what should it do? It should produce an angular acceleration. That is what we know from our 11th standard. In rotational motion lesson, we know that when torque acts on the body, then that produces angular acceleration. Force will produce a linear acceleration. You will have F is equal to ma. F is equal to ma. and torque is equal to I alpha. Okay, that is the equivalence. I is the moment of inertia of the body, and alpha is the angular acceleration. This moment of inertia about the axis of rotation or oscillation. Moment of inertia, you can have different moments of inertia for different axes of rotation. But let's not even get there. I just want you to remember this. Tau is equal to I alpha. So this tau is equal to I alpha. Then this expression is what I'm going to make use of here. This will be I into alpha is equal to minus mb theta. This is moment of inertia, and this is magnetic moment m, which is equal to NIA. You remember? So this is not mass. This is the moment of magnetic moment, and this is moment of inertia. So now alpha can be written as minus m b by I into theta. This should strike a bell. Okay? Look at this. This is a constant, and B is also a constant. The magnetic moment of this magnet would be a constant. The external magnetic field at that point would be a constant. And I, the moment of inertia about the axis of rotation, must also be a constant. If I take this magnet, for example, it's going to be ml squared by 12, because the axis of rotation goes through the center of mass. So this ml squared by 12 will be the moment of inertia. We all know that. So this is a constant, this is a constant, this is a constant. So I can say that alpha, this is directly proportional to negative theta. So this angular acceleration is directly proportional to negative theta. This is true only for small angles. And this is nothing but simple harmonic motion. So the definition of simple harmonic motion is that, right? If it is linear, then acceleration is proportional to negative displacement. You have studied that in your 11th standard. This is for linear acceleration, and for angular acceleration, this alpha should be proportional to angular displacement. Linear acceleration is proportional to negative of linear displacement, and angular acceleration is proportional to negative of angular displacement, which is theta. So this is a simple harmonic motion. And you may recall from your 11th standard that for simple harmonic motion, then if you remove this constant of proportionality, A can be given by minus omega squared x. And say for here, so alpha is equal to minus omega squared theta, where omega is the angular velocity, angular frequency, which is 2 pi f. So I can make use of this expression here. So if you make this comparison, angular acceleration is equal to minus mb divided by I into theta. So this mb by I must be equal to omega squared. So omega squared must be equal to mb by I. So then what is omega? So omega is equal to square root of mb by I. What is omega? Is the angular frequency, which is 2 pi f. So this is 2 pi f. This is omega is equal to 2 pi f, and it is also equal to 2 pi. F is 1 by t, the period. time period. So 2 pi by t, and that is equal to square root of mb by I. So I can find the time period using this. So if I take t there and if this comes here, so now t is given by, take it there. So 2 pi square root of I will come up and mb will go down. So this way I can find the time period of oscillation if I know the moment of inertia of the magnet and then the magnetic dipole moment of the magnet and B of the external magnetic field, not that of B, the magnet. Okay? So that I can find the time period. So in this case, the case that we're talking about, suppose I know the magnetic moment M of this magnet, and I can also know I, because ml squared by 12, as I said, we measure the mass and then measure the length, and ml squared by 12 will give me the moment of inertia of this ball magnet. And if I allow it to oscillate, and if I know the time period of oscillation, it is also possible for me to calculate B. If I know the magnetic moment M, and if I know the moment of inertia of this magnet, and if I allow it to oscillate now, and then if I calculate, if I measure the time period of this oscillation, then it is possible for me to measure and to calculate the magnetic field strength of the Earth magnetic field at this point using this expression. So how would I calculate B? I'll square it now. So t square everything. So I get t square is equal to 4 pi square into I by mb. So take it there. So B will be equal to 4 pi square I by mt square. So this way I can also calculate the field strength of the Earth magnetic field at this point. Hope this is clear to you. And now let's talk about the potential energy of this magnet in this external magnetic field. Okay, what is potential energy? For example, if you take this pen from this position to this position, then I do work against the restoring force of gravity. And the work I did against the restoring field is the potential energy of the system. mgh is what you get in the Earth, near the surface of the Earth. Anyway, so now it is at zero. Now this pen has zero kinetic energy, and at the final position also it has zero kinetic energy. But then there were two forces acting on it. One is gravity, and the other one is my force, as it was moving from here to this position. But there is no change in kinetic energy, which means that the work I did is opposite to the work done by gravity, and that is why the total work done is zero. That comes from your work kinetic energy theorem. So if you want to find the potential energy of this body, then what I do is that I find the work done by gravity, which was acting in the opposite direction and which was doing the opposite work. Then if I take the negative of the work done by gravity, then that gives me the work done by me. We have done that before. The same was done in the case of the electric field too. We're going to do it here too. So if we want to find the potential energy, what I should do is that I should find the work done by the restoring force, and the negative of that work is the potential energy of this body, because the negative of that work is the work done by the external force, and the work done by the external force is the potential energy, not the work done by the restoring force, the field itself. Okay, so we'll start doing it here. Okay, so what is potential energy? So potential energy is a work done by the external force or torque, okay, which is equal to the negative of the work done by the restoring field. Here I'll call this as the magnetic field. So if I can find the work done by the magnetic field and assign a negative sign to it, then that will give me the work done by the external force, in this case mine, and that is equal to the potential energy. So potential energy is not the work done by the magnetic field, it is a negative of the work done by the magnetic field, and that is true in every field. The potential energy is not the work done by electric field, it is a negative of the work done by the electric field, and the potential energy is not the work done by the gravitational field, it is the negative of the work done by the gravitational field. Likewise, here too, the potential energy is not the work done by the magnetic field, it is the negative of the work done by the magnetic field. Okay, so when I take this magnet from here to this position, then what is the potential energy? First I need to calculate the work done by the magnetic field, and the negative of that is the potential energy of it. Fine. Now what is the work done by the magnetic field? Well, the magnetic field B produces the torque minus mb sine theta, and from your 11th standard you know that in rotational motion the work done is given by integral torque d theta from some angle theta 1 to another angle theta 2. So this is the work done. This comes from your 11th standard. So I have the torque here, the torque of the field. Now I am going to find the work done by the field. So the work done by the magnetic field is equal to integral 2 into d theta from theta 1 to theta 2. Okay, this theta 1 could be 0 in this case, and I may take it to theta, but in general I can take it from any angle to any other angle, so theta 1 to theta 2. So I am trying to come up with the generalized version for this. Okay. So what is this tau here? Tau is minus mb sin theta. So that's equal to minus mb sin theta, okay, d theta from theta 1 to theta 2. So I can take the minus out, but you know, finally you get to minus mb. When I integrate this, m is a constant, b is a constant, sin theta is what will be changing. So sin theta d theta will give me minus cos theta, and then the whole thing, finally you need to apply the limits, theta 1 to theta 2. So what do you get here? So you get mb cos theta, then theta 1, theta 2. Okay, so this is the work done by. So if I expand it, then what do you get here? mb cos theta 2 minus mb cos theta 1. When you apply the limits, this is the final. But look at this, mb cos theta. How does it look like? It looks like vector m dot vector b. It looks like the dot product, right? mb cos theta. M is a vector, b is a vector. mb cos theta is actually m dot b. So I can write this as m dot b, and then I can apply these limits. So this is how it looks like. That's the work done by the field. But that is not the potential energy. Now what's the potential energy? Potential energy is the work done by the external force, the what I did. Okay? And that is negative of the work done by this. So potential energy is equal to work done by the external force, which is equal to minus of the work done by the field, and that gives you, if you apply to take this one, that would be minus, if you apply this, minus of mb cos theta, theta 1, theta 2, and in that case that will become mb cos theta 1 minus mb cos theta 2. Okay, so this is okay, I think it's clear, so I'm not mb cos theta 2 and minus mb cos theta. I can write this as, again, potential energy can be written as minus m dot b. Same thing, theta 1, theta 2. So this is the expression. So the potential energy is negative of minus m vector dot b vector. Again, once you've done that, you need to apply the limits. So this is what is the potential energy. Clearly, the potential energy will be this: mb cos theta 1 minus mb cos theta 2. That's the potential energy. So when it comes to potential energy, the energy difference, potential energy difference is important. For example, if in the case of gravity, let's say I take this pen from this position to this position. I can take a reference point like the ground, the floor, as my zero potential. Then let's say this is at height h1 from the floor. So I'll say the potential energy at this point is mg h1. And from this point I go to this point. Maybe like that is at h2 from the ground. So the potential energy at this point is mg h2. But the work done would be mg h2 final minus mg h1. This is how we calculate the work done there. And we are going to use the same approach here. What's this? I got this stuff. I got potential energy is equal to minus mb cos theta, theta 1 to theta 2. Those are the limits I have. Okay, now let me expand this. I came to the final result quickly here, but I'm going to expand it here. So the PE is equal to minus mb cos theta 2 minus the lower limit minus mb cos theta 1. So this is my final angle and this is my initial angle. I say this is my final potential energy and this is my initial potential energy. So this way I can assign a potential energy number to every angle. So I say that potential energy at an angle theta is simply minus mb cos theta. So if you go from theta 1 to theta 2, the potential energy at theta 2 is minus mb cos theta 2 minus the potential energy at theta 1 is minus mb cos theta 1. So this is how I assign a number to the potential energy at an angle. Okay? If you are going to take this approach, let us see what is the potential energy of angle 0. At angle 0, potential energy at angle 0 is equal to minus mb cos 0. Cos 0 is 1, so the potential energy at angle 0 will be equal to minus mb. Okay, what about potential energy at angle 90? So E90 is equal to, if I put cos 90, this is 0, so the whole thing will become 0, so the potential energy is 0 here. And what about angle 180? This side. So P 180 is equal to, cos 180 is minus 1, so minus mb into minus 1 will be plus mb. You notice here that minus mb is the minimum of all. So at 0 degree you have the minimum potential energy, and at 180 degrees you have the maximum potential energy. To go from 0 to 90, the work we need to do would be 0 minus of minus mb, which is plus mb. You have to do positive work to go from minus to 0. And from 0 to mb, to go from 90 to 180, then you have to do another mb amount of work. So mb minus 0 would be the potential difference between 180 and 90. And mb minus of minus mb would be the potential difference between 180 and 0. So if you were to take this approach, the potential energy of the field is, or the magnet, would be minimum at angle 0, maximum at angle 180, and then the potential difference between the minimum potential energy and the maximum potential energy is 2 mb. I hope this is clear to you. Okay, now let's do the example problem 5.1. Let me read it first. The magnetic needle has magnetic moment 6.7 into 10 power minus 2 ampere meter squared and moment of inertia 7.5 into 10 power minus 6 kilogram meter squared, and makes 10 oscillations in 6.7 seconds. What is the magnitude of the magnetic field? Okay, so clearly, even though it's not expressed here, they want the magnetic field of the magnetic field strength of the external magnetic field, not the magnetic field set up by this magnetic needle. So they want the B value of the external magnetic field. So we just came across that, we derived the expression too. So what did we say? We said the torques must balance, right? It is I alpha must be equal to m b theta. So we said alpha is equal to m b I into theta. Rather, it's minus really. It's a restoring torque. So omega squared is this. Omega squared is equal to m b by I. So omega is equal to square root of mb by I, and this is actually, what is omega? Or I don't even have to do this. Okay, I can go straight away from this expression. They want B, the strength of the external magnetic field. So this is equal to, what is omega squared? Omega is 2 pi by T, the whole square is equal to m B by I. So what's B? B is equal to 4 pi square into I divided by m T square. So they've given you the moment of inertia 7.5 and magnetic moment is 6.7, and then time is like for 10 oscillations is 6.7 seconds. So for one oscillation it will be 0.67. So if I put in all those numbers, it's going to be 4 into pi squared is roughly 10 into this is 6.7 to 10 power, no, this is actually I, right? 7.5 to 10 power minus 6, so that divided by, what are you going to have here? Here it's going to be m t squared. M is 6.7 into 10 power minus 2. 6.7 into 10 power minus 2. And this is going to be, this is 6.7 is for 10 oscillations. So for one oscillation t, it will be 0.67. So 0.67 the whole square. So this will be 4, and if you manipulate the whole thing, you are going to get 0.01 Tesla as per the book. So this is a very straightforward application of the formula. You know that I alpha is equal to minus mb theta for small oscillations, clearly, a small angle oscillations. So alpha is equal to minus mb by I, so omega squared is this, and then from this you can find b. So all the quantities are given in the problem, so you find the external magnetic field. This is not the magnetic field of the magnetic needle. This is the external magnetic field in which this needle has been kept. So that you have to be clear about. Hope you understand this. Now let's look at example 5.2. Let me read the problem. A short board magnet placed with its axis 30 degrees with an external field of 800 Gauss experiences a torque of 0.016 Newton meters. So what is the M? The magnetic moment of the magnet. That is A. B is, what is the work done in moving it from its most stable to its most unstable position? And C is, the board magnet is replaced by a solenoid of a cross-sectional area 2 into 10 power minus 4 meters squared and 1000 turns. The total turns is 1000. But the same magnetic moment. So the solenoid has the same magnetic moment as the board magnet. Determine the current flowing through the solenoid. So these are the three parts of the problem. So we'll take the first one, the first part A. What is the magnetic moment M of the magnet? Okay, first of all, what do they say? There is an external field. So there is an external field, draw it like that. Okay. And in that field, you have a magnet, a short bar magnet, making an angle 30 degrees with the field. This is the M, and this is B, and it is making an angle 30 degrees with the B. So In this, B is 800 Gauss. 1 Gauss is 10 to the power minus 4 Tesla. So this is 800 into 10 to the power minus 4 Tesla. So that's 800 Gauss. And the angle theta is 30 degrees. And the torque experienced by it is equal to 0.016 Newton meter. Then what is the torque? Torque is equal to mb sine theta. If theta is 30 degrees, then sine 30 degrees is equal to 1 by 2. If I substitute those values here, what am I going to get now? M I don't know, B I know, and sine theta I know, and torque also I know. Torque is 0.016. So I will put it 0.016 is 16 into 10 to the power minus 3. So this is 16 to 10 to the power minus 3. That is equal to M, I have no idea. And what is my B? My B is 800 10 to the power minus 4. And this is going to be equal to 1 by 2. Okay. So what does it give me? 810 power minus 4. So I can say 8 into 10 power minus 2. Okay. So this will be 4. So 4 and this one 16. That will be 4 again. 10 power minus 2. This will be 10 power minus 1. So M is equal to 4 into 10 power minus 1, which is equal to 0.4 ampere meter square. So that's the magnetic moment. So for the first part, the magnetic moment is 0.4 ampere meter square. That is the answer. Okay, what about the second part? The second part, B, is this. So what is the work done in moving it from its most stable to the most unstable position? And which one would be the most stable position? When it is making an angle 0, then this would be at the most stable position. Because if you disturb it slightly, then it will come back. It will try to come back to that position. Which is the most unstable position? 180 degree. Right now it is okay because it's aligned with the field. If you slightly disturb it, so this is the North Pole, okay, then it will go all the way here. So this is the most unstable position. Both are in equilibrium. This is stable equilibrium when it is 0. When it is 180, it is in unstable equilibrium. So 0 degree is your stable position and 180 degree is your unstable position. You are going to move it from the most stable position to the unstable position. And what is the work done? The work done here, that's the potential energy. So P E energy is equal to minus mb sine theta 2. That's the final position. Minus mb sine theta 1. So this initial position, this is the final position. So that would give me clearly sin theta 2 is 180. Oh, sorry, cos. I'm sorry. Cos theta 2 and this is cos theta 2. Okay, that's our plan. So minus mb cos theta 2, then here minus mb cos theta 1. So the cos, this theta 2 is the unstable position, which is 180 degrees. So cos 180 will be minus 1. So that will give me minus 1 into minus mb will be mb. Then minus this theta 1 is 0. So cos theta 1 is cos 0 is 1. So this is minus mb multiplied by this minus. So that becomes plus. So plus mb. So this is equal to 2mb. This we know. We have already done that. So this is equal to 2 into m, just found out to be 0.4 ampere meter square, and multiplied by b is 800 10 power minus 4, or it can be written as 8 into 10 power minus 2. Okay? So, this would be, I can write this as 4 into 10 power minus 1. So, this is 8 into 8, 64 into 10 power minus 3. So, this gives you 64 10 power minus 3, or 0.064 joules. So, this is the amount of what you need to do to move this magnet from its stable position to the unstable position, from 0 to 180. I should say this is 180 degrees and this is a 0. Okay. So that is part B. What about part C? Part C is the ball magnet is replaced by a solenoid of cross-sectional area 2 into 10 power minus 4 meters square and 1000 turns, but of the same magnetic moment. So we know that magnetic moment M is equal to N I A. Okay. Then determine the current flowing through the solenoid. What is M? It's 0.4. This is the M of the ball magnet, and that is equal to the magnetic moment of this solenoid. So this is equal to N is 1000 turns now. I, we have no idea. And what's the area? Area is given to be 2 into 10 power minus 4 meters. So 2 10 power minus 4 meters. Okay, so this I can write as it's 10 power 3 and 10 power minus 4. So I will write this as 2 into 10 power minus 1 into I. And this can be written as 4 to 10 power minus 1. So this 10 power minus 1, 10 power minus 1 can be cancelled. So I is 4 by 2. That is equal to 2 amperes. So that is the current flowing through the solenoid. It's not a difficult problem. Pretty much the straightforward application of the formula. So you can very easily do it. Hope it's clear to you.